I'm Dahan. This is by part 2. It is about server implementation, EfficientNet, and custom weights. So let's get started. Okay, so these are outlines for today's video. So first of all, we are going to work with the server implementation notebook and revisit PIT's dataset. Then we go through the EfficientNet model, create body for EfficientNet model, and the last thing is Pretrained PKL file. So let's get started. As you remember from the previous video when we talked about notebook dev, when this comment is included at the top of a notebook, it specifies that any code defined in that notebook should be exported to the deployment module by default. This means that any functions, classes, or variables defined in this notebook will be automatically available in the deployment module without the need for an explicit import statement. Let's now take what we had before and run inference based on a list of file names. So we'll make a quick script to get the ball rolling for how we want everything to do using notebook dev again. So first, let's install fastai library by using pip install. And then we import all the functions and classes from notebookdev.shodec. So if you forget, the notebookdev.shodec module provides functions for displaying documentation for functions, classes, and modules in a Jupyter notebook. Here we import the vision library from fastai. And if you work in Colab, you need to upload the style transfer Python file that we made in the previous video. So here we import it. Now we are going to use loadLearner function, which is used to load a model. The first argument to loadLearner is a pass to the exported model without the file extension. And the second argument is CPU, which is a Boolean flag that specifies whether to load the model on CPU or GPU. So as you can see here, we set it to be equal to false because we want to load it on GPU. And now we can make and prepare our data loaders with a file name. So as you can see here, we create our dataset, pass it our cat image, and we say that we want PIL image to create. And then we define our data loaders. So all of these works we saw in the previous video, so you can review it. And here we grab the raw value for our image and store them into this variable here. Okay, so let's wrap this into a function. So here we define our getLearner function, which is a simple wrapper around the loadLearner functions that we saw. Now we define our makeDatasets function that we'll use to create a data loaders object from a list of image file names and a pre-trained learner object. So it takes 3 arguments. The first one is a pre-trained learner object, and the second one is a list of image file names to be used as a dataset, and the third one, which is a batch size. So here we make it by default to be equal to 1. The function first determines whether the learner object is loaded on GPU or CPU. So if it is on GPU, so the function will set up an after batch transform that normalizes the pixels values of the images and converts them from into plot tensor. And if it is on CPU, so the function will set up an after batch transform that normalizes the pixels values of the images, but without converting them from into float tensors. And finally, the function creates a data loaders object by applying the after item and after batch transforms to the datasets object and setting up the batch size and the device. Then we import save image from Torch Vision. And now we can write a quick save image function to save all our output tensors to images. So the function takes 2 arguments, images and path. Images is a list of images in form of a tensor object with dimensions n, c, w, and h, where n is the number of images, c is the number of channels, w is the width, and h is the height. And for the path is a directory where the images will be saved. So the function uses list comprehension to iterate over each image in the list and save it as a separate image file in the specified directory. So the image file names are generated by concatenating the index of the image in the list with a .png file extension. And now let's put it all together. So here we define our inference function. So the function first creates a directory within the specified path to save the output images. And then it loads the pre-trained model using getLearner function and create a list of data loaders object using makeDataset function for each image and file names. The function then loops over each data loaders object, performs inference on the batch of images using loaded model, and saves the resulting predictions as a separate image files in the output directory using saveImage function. Now you can go and play with that, so you can try it on any image you want. Okay, so let's go ahead and get into something more fun and can be applied anywhere, which is EfficientNet and custom pre-trained models. So what we are going to cover here is how to use any sort of PyTorch model, their pre-trained weights, and set it up to how CNN learners build their models. So the problem today will be familiar one, so we are going to revisit PET's dataset that we saw in the previous video in our series. And as you can see here, we install fastai library by using pip install. And here we import vision library as we saw. And then we are going to grab our dataset by using enter data method. And here's our transformations, and we are going to use a batch of 64 images. Then we define our data blocks, so we are going to use image block and category block. And here's our data loaders pass it our path to of the images along with a batch size. Then we show a batch of 9 images from our dataset. For today's task, we are going to focus more on the models as I told you, so let's focus on our EfficientNet model. So we'll be working out of ROS repository. Here's the link. So included in this repository is tons of pre-trained models for almost every major model in computer vision, all were for 224 by 224 training and validation size. So let's install it. So as you can see here, we install it by using pip install. Then we can use his weights by using one of two ways. First, we will show the direct way to load it in, so let's go with that. So here we import our create model, which is used to create a pre-trained convolutional neural network model for image classification tasks. So as you can see here, we create pre-trained EfficientNet P3A model, and we initialize it with pre-trained weights. Now let's take a look at our downloaded model so we know how to modify it for transfer learning. So here we build our CNN learner, pass it our data loaders and ResNet 18 architecture. And if you notice here, we have a custom head that has adaptive concat pool 2D. And if we do this in our net, which is our efficient net, as you can see, we doesn't have a head for our model. It doesn't exist. So most of the time when you try this, you will get this error here. Now let's see why we have this error. So when we made our head, we create two different groups. Group 1, our encoder, which is everything but the last layer of our original model. Group 2, our head, which is the fast AI version of a linear layer, plus a few extra bits. And for our efficient net, it doesn't have these things, so let's fix this. So if you look at EfficientNet Model and go down, we can see that we have global pool and linear layers as the last two. Okay, so now let's go and create a body and see what we will get. So here we call create body, pass it EfficientNet, and the pre-trained equal false argument here specifies that the weights of the model shouldn't be pre-trained, and the cut equal -1 specifies that the layers of the model should be included in the body except the final classification layer. And as you can see here, we have this error. So let's see why we have this. Okay, so if we take a look at how create body expected, so it expects our architecture to be some sort of callable function and then it cuts. So as you can see here, the function first creates an instance of the model specified by architecture. It then determines where is the cut of the body of the model using the cut argument here. Then the function returns the body of the model, which is defined as all layers up to the point of the cut. So if the cut is an integer, the function uses n.sequential module to return all layers up to the cuts layer. And if cut is a callable function, so the function applies the function to the entire model and returns a modified model. And the last thing, if the cut isn't an integer or a callable function, so the function will raise an error. So we can see that architecture needs to be a generator. So let's try to make a function to help us with his library. So here we go ahead and call a create model, which is a function that we declared earlier. And the other parts of the code are the same as create body that we saw above. So let's try it out with EfficientNet B3A. So we can see that we have 7 different groups. If we take a look, you can see that we have 0, 1, 2, 3, and if we go down, you can see that we have also 4, 5, and 6. And now let's move on to our head of the model. So as you can see here, NF computes the number of outputted features of the last convolutional layer in the body module by creating a new NN.sequential module that contains all the child modules of the body module and passing it to the number of features model function. And the resulting number of features is assigned to the variable NF and returned. And this times 2 here because our heads uses 2 pooling methods, average pool and max pool. And here we create a head out of these, so we pass it our NF variable, and then we declare that we want our output to be number of classes that our data loaders expected. And finally, we just wrap them together into neural net sequential. And here we initialize the weights of the second child model of the neural network model using Kalman normal distribution. And as you can see here, we have 2 layers. And here we make our learner pass it our data loaders, the model, and the loss function. And if we take a look at the summary, so here we have a problem because it didn't pick up that we have some non-trainable parameters. So why is that? Because CNN learner will also call freeze, which will freeze up to the last split. So to fix this, we need to pass a splitter for our learner. So here we use the default splitter. So if we call freeze after making our model and look at the summary, as you can see here, the head of our model is trainable and our encoder or ResNet is non-trainable. And then we can find our learning rate as we used to do and train our model for 5 epochs. So here we save the model and then we can unfreeze it and train it a little more. And here we train it for 5 epochs again and then we save it. One of the hardest parts about training the EfficientNet models is figuring out how to find the right learning rate that won't break everything, so choose cautiously and always a bit lower than what you may want to use after unfreezing. And now let's go with something a bit more different, which is what we do if we don't have the library that Ross made and we just have some pre-trained weights. So we are going to take our cats and dogs model and try to train ImageWolf dataset on it. So this goes ahead and grab ImageWolf dataset for us, and then we defined our transforms that will be applied to it. And then we made our dataset and our data loaders, and as you can see, we are going to use a grandparent splitter. And here is some batch of our data. Okay, so first let's grab our model and make our learner like we did before. So as you can see here, the body of the function is created using createTempBody function, and the head of the model is created using createHead function, and then the model is constructed by combining the body and head using an ended sequential. And lastly, the weights of the head are initialized using the common normal initialization method. So here we build our learner, pass it the data loaders, the model, and the loss function. And we are going to use a default split as our splitter and the accuracy metric. And now we want to load the weights from the previous model into the new model, and if you try to call learn.load here, you will get size mismatch error. So let's try something else. So all the weights of all of our layers are stored away into state dictionary. So here we call it. And we are going to use a technique that Variate made on the forms. So here is the link, you can go and check it. So here we are accessing the model dictionary attribute of our learner. So the model dictionary is a path where the trained model will be saved or loaded from. So as you can see, here is the path, which is models. And this is the function that Variate made. And what we do is just we pass it the learner, and the name argument here represents the name of the pre-trained model to be loaded, and the device object represents the device CPU or GPU on which the pre-trained model will be loaded. And here we grab the state dictionary from the new model, and then we also want our learner state dictionary. From there, we are going to check in all of the current dictionary if anything on our learner's dictionary is also in our new dictionary. If so, we are going to copy the weights, and if not, so we are going to skip it. And if it is not even there at all, so we will say that it wasn't there. And finally, we will load the transferred state dictionary into our learner and return it. So if we call transfer learn and pass it our learner and the stage 1 that we made earlier with dogs and cats, we can see that we get a shape mismatch at 1.8 weight. So what that mean? It's just an index. So if we index our model at 1 and 8, as you can see, we have a linear layer where we have our in features are 512 and our out features are 10. So now we can freeze our model. Let's now see if this works. So we will do a comparison test between 5 epochs without our transfer learn and 5 with. And here we train it, so this is our transferred model, so we get about 89% accuracy. Okay, so let's try it on a regular non-transferred model. So here's an example for non-transferred model, and as you can see here, we have about 15% accuracy. Okay, so this is how you can transfer over any sort of model you want. So that's it for today's video. Hope you enjoyed.